Okay, so yeah, thanks everyone for coming along. So yeah, as Ollie said, I'm going to talk to you about Ratpack, the story so far. So as an agenda, basically the Thor team in Cirrus building a new microservice, and we decided, as you'll see, to use Ratpack as opposed to DropWizard. So that's kind of interesting because it was new to us and new to you guys, hopefully. So yeah, and this is just a bit of knowledge sharing, really. So first of all, going to talk about what is Ratpack, not a full-on Ratpack tutorial, but just kind of an overview. Why did we decide to use it? A look at the code, and then when things get exciting, look at the mistakes that you can make, the issues that we currently face, and then a little bit of a retrospective as well. So first of all, what is Ratpack? So it's a high-performance Java web framework, asynchronous and non-blocking model. It basically aims to make asynchronous programming on the JVM easier. So at its worst, asynchronous programming can be basically described as callback hell, where you have a whole ton of blocks of code, and it's very difficult to reason about what gets executed in what order, and things seem non-deterministic. So Ratpack aims to address that problem. It's built on Java 8 and Netty, and it's currently at a nice stable version of 1.1.1, but actually relies on a beta version of Netty, which is interesting. Assuming your application is I/O bound, it offers the following benefits. Basically, high throughput can be achieved with low CPU usage and low memory usage due to the less threads, and this is all basically down to its threading model. So given that your application is I/O bound is an interesting statement. So there's sort of varying degrees of that. If you're writing an application that, okay, it does perform some I/O, but it only spends a very small number of milliseconds contacting that I/O, say maybe Cassandra, and it's local and it's running very, very fast, perhaps you're not actually going to get these benefits. If you're calling something which is basically, the more your application is spending waiting for I/O, the more potential benefits that you can realize with Ratpack. So just sort of a recap, really, of synchronous blocking versus asynchronous and non-blocking. The synchronous blocking model is what I'm most familiar with, and everyone on the team is most familiar with. So, I'm used to DropWizard. People familiar with DropWizard? Show of hands use DropWizard. So yeah, a lot of people have used DropWizard here, and old Servlet API, Tomcat web apps, and so on. All follow the synchronous and blocking I/O model. It's kind of like the standard. So you have method A, which is a little bit of computing, and then very quickly we make a HTTP request, let's say, to a downstream system, and that is then basically this thread is now blocked, waiting on I/O. And all of the time that this nasty red area here is happening, that thread can't do anything else but just wait for the response until finally it can execute method B. So the problem with this model is that how do you keep the CPU busy? How do you process other requests at the same time? We're talking web mainly. How do you process other HTTP requests at the same time? The answer is you have more threads. That's the way that you get the increased concurrency. The problem with that is that since this thread is blocked, the JVM will have to switch from one thread to another, and switching from one thread to another is basically work in itself. And the more you do that, the more of a tax there is basically on your application. So with the asynchronous non-blocking I/O approach, we have method A that kicks off the call to the downstream system, let's say a HTTP request, and it instantly completes, and the thread is not blocked. So here we see that the thread can do something else useful. It can't run method B yet because obviously we haven't got the response yet, but the thread can do something else useful. So in the previous example, what we have is the thread is blocked and the JVM has to switch from one thread to another. In this example, the thread is not blocked. The thread can switch to processing another task, another execution. So obviously, for it to do that, you have to code in a different way to facilitate this. So method B is basically a callback that will get invoked once this returns. So the increased efficiency of this model and using Ratpack comes at a price, and that is a steep learning curve. It's easy to get wrong, and it's also can be quite hard to debug as well, as you'll see. So some of the misconceptions. So in talking about Ratpack amongst the team, other people would hear things, and they'd hear phrases like, "Oh, everything is asynchronous," and people would get a little bit confused about that. So the asynchronicity, which is a word, is internal only to the web server. It's just a HTTP web server that you're building in Ratpack. It's still going to take time to, if you're a client sending a HTTP request, doesn't need to do anything fancy whatsoever. It's still going to take some time for that HTTP response to come back. It doesn't improve latency. If your Ratpack application has to talk to something that takes 500 milliseconds to respond, you're not magically going to remove that latency. Although there is a case that you can actually use the streaming API, whereby you actually start sending the response before you've actually received all of it. That's not something that we've had any experience of, and I don't know much about, but it is true. You can do it. And also, it doesn't necessarily mean that if you're using Ratpack, it means that your system is going to outperform a Dropwizard or Tomcat web app. In actual fact, there's a lot of ways that you can make it actually perform a lot worse. So why did we decide to use it? So we basically are building a service that talks to many downstream systems which have latency. They take typically, say, 100 milliseconds to respond. And what we decided to do was to see how much benefit could we actually gain from potentially using Ratpack. We spun up two sort of dummy applications of what we intended to build, one in Ratpack and one in Dropwizard. And this is basically what they do. So the application here sends a request to its downstream system. In this case, we just used WireMock. Are people familiar with WireMock? I'm guessing, yeah, cool. So yeah, WireMock was just primed to have a slight delay and then return a response. And then we started running this at high load. And we then realized that actually WireMock was the limiting factor, so we actually had to distribute the load across WireMock so that to remove that bottleneck, just so that we could purely test the application. So that's why we have an ELB here. And when the response comes back from our downstream system, we just had to filter out and do some sort of string manipulation to a JSON response and then send that back to the client. And that's basically, in a nutshell, that's what the application that we're building will be doing, obviously with a lot of extra functional requirements than that. So we hit it with 3 different load profiles, all 5 minutes in duration, 100 concurrent requests, then 200, then 300, and then looked at the results. So the first 2 runs, so 100 concurrent and then 200, were kind of the same. So Ratpack had the edge; it did achieve slightly higher throughput, and then run 3, we found that Dropwizard actually gave up halfway through. So this would indicate, quite positive. Fantastic Ratpacks. These are all obviously running on the same machine. I can't remember what machine it was, but it's a apples for apples comparison. So yeah, you can see here that it appears that Ratpack can take more throughput basically on the same hardware. The memory, so this is a little bit confusing. So we have for run 1, you've got the minimum and the maximum, and both of those are lower than the Dropwizard equivalent. And then the same for run 2 and the same for run 3. We are theorizing that this is basically down to the number of threads, which I'll get to in a moment. The CPU load as well is a lot lower, and so this can basically be explained by the fact that the JVM isn't having to switch from one thread to another as often. It does still do that, but just not as often as the Dropwizard equivalent. But then the really fascinating one is the number of threads. So by default, Ratpack will tune itself to have a number of threads which is 2 times the number of cores on the actual machine. So the idea is that you can't hope to really achieve any more throughput by adding any more threads, because if you're non-blocking, those threads shouldn't have to be switched out. The threads should be computing all of the time, and if you can't compute all the time, then adding another thread is not actually going to solve any problems. So yeah, this is quite amazing, and also obviously the lower number of threads also explains the decrease in memory as well. Should also point out as well that the memory graph here is just looking at the heap. which was a bit of a mistake. We should have looked at memory off heap as well, because Ratpack and Netty, I believe, actually uses a lot of memory off heap, so that wasn't really quite a fair comparison. DropWizard apparently, and its associated libraries probably wouldn't be using that much memory off heap. Okay, so as I mentioned, we will be IO bound. This is why we decided to use it. We'll be at high load. So we're hoping for in between half a million to 3 million concurrent users, which would be either 1,750 calls per second or 10,500, which are huge numbers. But those estimates seem to be changing as we go on. So yeah, we're going to be at high load. The performance test obviously revealed really encouraging statistics, and we also had a sense of optimism that we pick up the asynchronous challenges. One of the things that also is quite funny was that the people behind doing the spike and looking into it were probably some of the smartest people that I've ever met. So maybe a little bit false sense of confidence there that we pick up those asynchronous challenges, but we did okay, as you'll find out. So sorry, a look at the code. So for all of the differences of Ratpack that make it kind of unfamiliar, there are some similarities with using, if you're familiar with the DropWizard world, you can bundle it all up as a runnable jar. It doesn't need anything installed like the good old days of Tomcat or any other, web servers. You have a nice main method that just starts up the server, so it can be very easy to. One of the things I absolutely love about DropWizard is that it's so easy to test. You can just one unit test can start up the DropWizard application, and you can fire a HTTP request at it, which I think is just amazing. And the same thing can be said for Ratpack as well, which is really useful. So where it gets different, so URIs are mapped to handlers. So I'm always sort of thinking in the JAX-RS, sort of standards, whereby obviously you have annotations that map your HTTP requests to the incoming Java. Ratpack does not support JAX-RS, so instead we have handlers that are mapped using a notation, which you'll see in a moment. Handlers can be thought of really more as filters or interceptors, in that a handler can basically be multiple handlers can be applied to the same request. So you can have one handler that, say, some sort of logging interceptor or something like that every single HTTP request will go through, and then you can nest handlers. The execution model deals with promises. So because you're writing in an asynchronous way, you need something to deal with this. So it's not as simple as if you've got a, in the good old days, that we have, if you have a method that calls a database, get value from DB, it returns what it comes out of the database. You can't have that in Ratpack or the asynchronous model. You have to have a promise of what will be returned from the database. So that's where things start to get confusing for me, because I don't actually have that much background with asynchronous programming. So this was where the learning curve really started to kick in. So if you were to return the actual value, that can only be a blocking method, because if you didn't have it before and you have it at the end of that method, how long is that method going to take to execute? It's going to block. So you need methods that return instantly with promises that that this object will emit that value later on. So promises are a Ratpack concept, but there are many other objects for this sort of thing, something that will emit a value later on, such as futures. So if you've used Cassandra, you'll know about result set futures. It will give you a result set later on, or also RxJava observables. So what we decided to do was, because we were anxious about using Ratpack, we didn't want to completely jump into the swimming pool and have no way out at all. We wanted to basically not bake in dependencies on the Ratpack framework throughout all layers of our code. With DropWizard, your dependencies on DropWizard are hopefully mainly just at the resource layer, right? Just at that sort of front end, and then as you go into your service and your DAOs and other objects, there shouldn't really be many dependencies, or if any dependencies, on DropWizard. But with Ratpack, the path of least resistance was for us to use promises, which would bake in those dependencies all the way in. So we decided to use RxJava's observables for our object that will emit a value later on, essentially. And we decided for that as well because we're using Hystrix as well, which also uses RxJava. So it felt like a good choice. So a look at the code. So a HappyPath example. Let's have a look at this. So here we have a a server, and you can see here we have a main method, so nothing at all special about that. I'm instantiating the objects myself. I'm not using Juice, but there is really good integration with Juice with Ratpack. And then lower down here we see the configuration, so I'm just telling it to start on port 8080. And then down here we have a handler chain. This is very, very flat for my demonstration, but basically the path happy will be responded to by this happy handler. And so yeah, this line of code here just starts up our server. So let's have a look at our happy handler. So this handler implements the handler interface, which you can just have a quick look at, is a functional interface. It's got this non-blocking annotation, which is just basically a reminder, please don't make this blocking, but you can make it blocking if you make a mistake. And so because this is a functional interface as well, it means that you can actually define your handlers in just one line. So this here could actually just be replaced by a lambda. And there are actually some really nice examples on the net of people who have made kind of sort of non-trivial applications in one class, and it actually doesn't look too bad because you can just define these lambdas that define the handlers. So this API is actually quite succinct, and to be honest, you'll pick this up. If you choose to go with Ratpack, you'll pick this up very, very quickly. It's really not that difficult. So where it gets more interesting, so we have our HappyPath service. So what I've got here is we're making a call to a downstream system, which in our case is WireMock, and what WireMock is going to return is just a HTML response, just one tiny little message. And as I mentioned before, this can't just return a string. It is returning an observable of a string, so it will return a string later on. So if I go back to my happy handler, so we've got our observable of a string, so this will give us a string at some later point. So this method will be called straight away and return straight away, even if there's a 3-second delay on the actual downstream system. This will still execute straight away. We then convert that observable back to a Ratpack promise. So the way in which you notify Ratpack that you have more work to do is by basically creating a promise and calling the then method on it, which notifies Ratpack you have some work to do before you can say that this request has been finished. So what that means is that let me have a look at the context object. So the context object as well up here is basically just has all of the details for the request and the response, and it's basically a context. So a HTTP request gets mapped to an execution. So this here is, we're in this method here, we are in that execution. And then that execution is then divided up into multiple execution segments. And this here is an execution segment. And this is a separate execution segment. So this execution segment here won't be actually invoked until the HappyPath service has actually returned its thing. So we can have a look at this. My downstream HTTP server, which I have configured here with WireMock, is just all I've got. Hopefully this should just be really not much of a big deal. So yeah, we've just got a fast endpoint that takes 100 milliseconds to respond, and then a slow endpoint which takes 3 seconds, and all it does is just returns the body yay. So if we go back to my handler, my happy handler, so this downstream HTTP service, let's have a quick look at this. So this is using a Ratpack HTTP client. So this is a HTTP client that obviously comes with Ratpack, and it's non-blocking. So what this does, this is where it gets a little bit confusing. So the Ratpack HTTP client just takes a URI, and you can call get, and it returns a promise of a received response. Now, I mentioned earlier on that we didn't want to bake in promises into our code base everywhere, so what is common for us to do in our code base is to just keep this as an internal implementation detail and then convert it to an observable and return it. So we have a promise of a received response, but what we want is an observable of the actual string content that has actually come back from our downstream system. So what we do is we just call the map method on observable, which allows you, sorry, first of all, we convert it from a promise to an observable, which is this line here. And then once we've got that observable, we then call map, which is just saying, if I have an observable of received response, how do I convert to an observable of string? And it's just received response.getBody.getText. So we can have a look at this in action now.
Sorry? Yes. Yeah, basically, yeah. Sounds really good about them. Yeah.
Hey everybody, Phil's lost connectivity, so we're just getting this set up again. Stand by.
Yeah, so yeah. That's what makes it more difficult. So the theory is basically no one's directly saying
Is it working now? Is that good?
yeah.
So that's fine. So
Screen sharing on.
you hit your
This is touchscreen, so because
so it's screen sharing.
okay, cool. Hopefully back in business. Okay, cool. So yeah, yeah, sure. Okay, so what we can do is we can just run this requesting again. So let's actually just do this in. I always click the wrong button here. Okay, so what we'll do is now we'll just hopefully you've seen the log.infos. So request received, and then once we actually get the response, we emit this item here. So response sent to client. So if I go back to good old curl, which is curl localhost happy. So you see the first event that comes in straight away is request received, and then you see that we get our response here, downstream system returned yay, which is exactly what our handler is doing here. So yeah, you can see that the first event was as soon as we sent the request, and then the last one, this next execution segment or callback, happened basically 3 seconds afterwards. Okay, so that's very exciting, but what about at high load? So rather than spin up a full kind of JMeter performance test, what I thought would be more interesting is if we just go back into my app, you might have noticed earlier on that I've tuned Ratpack to only have one thread. So what that means is it will yeah, just that, it will just have one compute thread. So if I send 4 requests at this at the same time, what do we think is going to happen? So let's find out. So we have a if I just clear this context here, so okay. So 4 simultaneous call requests, HTTP requests to the happy URL. 1, 2, 3, and they all return straight away. So if we go back over here, this is the magic, I think. We see we have 4 requests received, all within the same, almost the same millisecond. and all on the same thread. And then down here, we have the same events, got response from downstream, response sent to client, all again on the same thread. Magic. I find that really amazing. It really does blow my mind. Hopefully that makes sense. So the other thing I wanted to show you just before we move on to the more exciting things of how you can mess everything up is a deterministic example. So I mentioned at the start of this that Ratpack aims to reduce the chance of callback hell. It doesn't completely eliminate it for sure, but one of the things that that can happen in asynchronous programming is basically race conditions. So here, this is basically the happy handler, but what I've done here is I've actually put in basically a line of code that says send a 500 error to the client. So at this point here, what's going to happen is this going to take precedence over this? And what about if the downstream system only takes 1 millisecond to respond? What if there's some other processing here, so a thread.sleep that takes 1,000 milliseconds? So typically you can have race conditions. Ratpack does not in this situation, because the idea is that the Ratpack promises are only activated once the handler has actually completed. So this will always win. And basically have a test that proves that. So yeah, happy deterministic functional test. So yeah, we just send a HTTP request and just guarantee that it returns a 500 response. The other thing that I wanted to show you just very quickly as well is that this here is just using kind of the standard sort of JAX-RS and Jersey client to send to, because it's just a functional test. Just use your favorite HTTP client, and you can also see here. So I'm just starting up my wiremock stubs here, and then this is my this is basically my application under test. So Ratpack comes with a really nice way of being able to just start your server up in one line in your JUnit test, and that test runs really nice and fast. Okay, so let's go back to presenting. So we've had a look at the HappyPath and high throughput and deterministic. So the interesting stuff, mistakes that you can make. So there are basically two different types, I think, of mistakes that you can make. Dangerous ones and annoying ones. So the dangerous ones, you don't know that you've made them, and you find out later on. This is more true for us, I think, because we're evolving our NFT, our performance tests at the same time that we're developing. So maybe not as much of a problem if we had those really up to speed. But yeah, you can basically find out problems a lot later on. And annoying mistakes are the ones where it's immediately obvious that you've got something wrong because it just doesn't work, but you just can't understand why, and you end up spending hours and hours or days and days working on something. So the dangerous mistakes. So calling a blocking method. This is the really interesting thing. So if we have a look in my app, you'll see here what we've got is a handler called the DAO handler, and all this does is it calls a DAO. This is just one interface that just returns an observable of string. If I go back to my DAO handler and just converts it to an observable and just says db returned and then the value. So if we now have a look at my app, see that I've got 4 examples. The top 2 are blocking, and then the other 2 are non-blocking, and there's slight variations. So if we have a look at this, so the DAO handler here is calling the blocking obviously DAO. So if we have a look at the blocking obviously DAO, who can tell me what the problem is with this code? Anyone? Yeah, exactly that. Yeah. So just pointed out that basically the get is a blocking call. So we have this nice occurrence of a method that sounds very comforting, execute async. Oh yeah, nice, we're all asynchronous, but then we just call get and then we block on it. So yeah, very bad. So second question, what's the impact of this? So given I'm using stubbed Cassandra here, and I've primed. I won't show you the code, but I've primed stubbed Cassandra to take 1 second to respond to any request. And we only have one Ratpack thread. What's going to be the impact of this? Can anyone think? Pardon?
No more processing if thread is blocked.
Yep. So let's have a look. So what we can do is, so we've got my DAO blocking, obviously. So I'm going to copy that and put it into Terminator. So, okay, thank you so much, Terminator. You've really screwed that up. I think that is correct. So anyway, let's press enter. So 1, 2, 3, 4. So just randomly, the top right client up here had to wait 4 seconds for the response. So what we've done here is we've got one thread. It should be able to deal with hundreds and hundreds of requests simultaneously. But what we've got now is we've got the worst of both worlds. We've got the synchronous blocking code in an application that only has a very small number of threads. I've tuned this down to 1 thread just to sort of make a point, but in a real life example, it would only be 16, which isn't really that much more anyway. So you've basically got yourself a drop wizard application that has a tiny number of threads, which is absolute disaster. So you should be able to detect all of these things with your performance tests, but you need to have great faith in your performance tests, because you could have a section of the code which, it's not going to be executed very much. That's probably going to be 1% of our calls. But if it's blocking, that can then affect the 99% of other calls. Because whilst this request was going on, I'm not even going to be able to hit the info page. And the info page doesn't even do any I/O. It's just a, let's say it's a handler that just says return hello world. That's still going to be blocked in just the same way. Okay, so the interesting thing is that I did this talk a couple of weeks ago to the Cirrus team, and I presented, this is the bad code, as I just showed you, and this is the good code. This is the code that works. And then someone in the audience, Chris Beatty, very clever guy, pointed out, actually, that is also wrong. And we didn't realize this. So this code here is converting a result set future into an observable using this method that just comes from RxJava. And you'll see that although this method, we patted ourselves on the back that we weren't blocking in this example because we're not calling .get, okay, as we were earlier on. So actually this method is not blocking. But when somebody subscribes to the observable that this emits, it does block. So this one is just as broken, just in a different way. So the actual offending line is from here. This is, yes. So this is it's a future, and the future is just very simple. It just has .get, and there's not really much else that you can do with it. So what this is actually doing here in RxJava is it's just calling .get under the hood. So when you subscribe, you're going to be blocked in just the same way. So if we now go back to my app. The non-blocking hot DAO, so I'll describe the difference in between hot and cold in a moment, but this one here, we think now, and I think I've proven it with the test, is actually non-blocking. So what we're doing here is we are using the another library called RxJava Guava, which is a very small library, which is just to convert between Guava's listenable future and the Rx's observable, and so the listenable future is more advanced because it actually has a callback as to when that downstream when that thing has completed, basically, and so this bit of code here will adapt from that in a non-blocking way. So it's all very well and good me saying, I'm pretty sure that this is absolutely fine, but the best way to actually prove it is, like anything, with a test. So I think I've got a test which reliably shows us if this is actually blocking or non-blocking, so I can hopefully run that now. So essentially what I'm doing here in this non-blocking hot DAO functional test is I'm sending 8 requests at the same time, and making sure that the whole So yeah, send 8 requests to the handler at the same time and make sure that they respond quicker than the absolute maximum that they could take, which is the Cassandra delay in milliseconds multiplied by the number of calls. So this is just a class that I made, this concurrent executor. All it does is it just takes a task and a number of times to do that task. We create a thread pool, which is the same size as the number of calls we want to actually make, and we just kick off all of those requests at the same time in parallel. So when I run this, you should see the test pass because the timeout. So if we look at the failing one, blocking obviously our functional test. So this is ignored because it is blocking. If we run this, this should fail for exactly the reason that it's taking too long. So you can see here that this is taking a long time, and it's going to take too long. So test timed out. So this is a way to really safeguard yourself into making sure that you're non-blocking. And I think that really, to be honest, it only makes sense to do it right at the front end level, at this kind of sort of functional test level, just because there are just so many intricacies and into ways that you can get things wrong. Okay, so other mistakes that you can make, you can create new threads. This will work absolutely fine. It's dangerous because I didn't put this in red, maybe not as dangerous, but it is still dangerous because basically you're just going to increase the memory and the CPU usage, which is very, very sad because all of the benefits of Ratpack are going to be lost. So all the extra time that you spent learning the new framework and battling with the asynchronous programming model are going to be lost if you start spinning up new threads all the time. Yes?
In your code examples, you used data stacks driver which could make asynchronous calls, or did you have only a driver which does only blocking operations without creating new threads?
Yeah. So the first thing to do, so the question was in the example that I had there, we're using calls to data stacks Cassandra, and it has asynchronous support. So what if you're using something that doesn't have asynchronous support? So the first thing would be to look at how could you get asynchronous support for your downstream system. That would be like the primary goal. Secondary is Ratpack does actually have support for making blocking calls, but the way that you do it is you give a runnable to a different thread pool, different executor service basically, and Ratpack has earmarked those as, right, okay, I know these guys are going to be blocking. If you just do them in line on the Ratpack compute threads, that's when things are going to start going all wrong. So there is support for that, because otherwise you wouldn't be able to use JDBC and other things that are blocking. So yeah, this one here is dangerous because you have the impact of increasing the memory and CPU and ultimately low throughput again. Annoying mistakes, so something that we found, which I'm not going to talk about in that much detail, but not understanding the execution model. So when I talked about how the execution is broken up into multiple execution segments, when we got that wrong, our handler was completing instantly, and we were getting an error that said, hey, you haven't sent a response. And then a second invocation would then send a response, and then it would have another error. Hey, you're trying to send 2 responses to the same client, and that was basically just because we didn't understand the execution model, and it really does take a long time to do that. So I've got some more stuff on my blog as well about that mistake. Yeah, we've also had some other really interesting things as well. We've messed up the threads massively. So we've had the Cassandra. When we were looking at getting the listenable futures converted into observables, we had a situation where the callback from the successful operation from Cassandra, that thread was then being used to do other useful work and then call Cassandra again. So it's like we're kind of stealing Cassandra's thread and then using it to make another call, and then things started getting very, very confusing and strange, and it's probably not the way it was designed. So yeah, that was another annoying one that just took us a long time to kind of figure out. So issues that we currently face. So really surprisingly, the Ratpack HTTP client does not use a connection pool, which is kind of weird because it's a whole performance-oriented stack. But yet this HTTP client that I just showed you, it will open a new connection every single time. So if you're calling a downstream system that is using TLS, then that's going to be quite an overhead as well, obviously, because it needs to establish a new session. So that's very bad. Not quite sure if that's a big enough problem for us to fix it or investigate an alternative. non-blocking HTTP client. Also, the App Dynamics integration. Probably you guys have all heard of App Dynamics, so yeah, we're still trying to integrate it with that, and we are actually going to get someone from App Dynamics to come in, and we're just going to bombard him with talk of observables and promises and Ratpack until he passes out or fixes the problem, hopefully. Other issues that we've had, so really interesting one, we had at high load, 1 in 1,000 requests would just not get a response. So normally, what do you do in that situation, right? You've got, this one's just waiting for a response, let's do a thread dump. Well, the thread dumps revealed that nothing was blocking because it's all non-blocking. So where do you go from there? It was very, very confusing. It actually turned out to be an issue with running Ratpack within IntelliJ IDEA, and we didn't realize that we were running in development mode, and we were convinced that we weren't until we then heard about this line of code deep in the Ratpack source that actually looks and sees if the command has the word IntelliJ, on the class path, and then it starts running in development mode. So yeah, that was a little Easter egg for us. So yeah, a retrospective. It was harder than we expected to learn. And it took longer than expected as well to get up to speed. So we had a really funny situation where it's almost, well, funny I suppose, maybe not the right word, but each retrospective, the question would come up like, well, why are we so much slower? When are we going to sort of speed up? And we're like, don't worry, I think we're over the learning curve now. I think the next sprint's going to be good. I think we've got it. And then the next sprint would be just as slow as the one before. But yeah, it's still taken us a very, very long time, and even just 2 weeks ago, we're still learning fundamental concepts of converting these result set futures to observables correctly. RX definitely, I think it has brought us flexibility, but it's introduced an extra learning curve. So I don't know if maybe we would have been better off just accepting that, well, we're going to have to rewrite the whole thing anyway if we give up on Ratpack. So maybe we should have just used promises everywhere. Not sure. The cost versus reward analysis we didn't really do. So we mentioned obviously that this is going to be more efficient, but how much money is that actually going to save Sky? How this lower CPU and the lower memory, does it actually really justify spending 2 times as long doing creating a Ratpack application? Yeah, it's a difficult question to answer, but it's still, I would recommend that if you go to use Ratpack, even though that's a difficult question to answer, try and answer that question as best as you can. And it doesn't matter if you're based on assumptions that are completely incorrect. It's still worth getting it all down on paper and saying, well, 2 months ago we thought this and we thought this, and so we thought that, yeah, we're going to save a lot of money. So yeah, it's definitely the right thing, or not. Monitoring our CPU and memory usage is key to realizing the benefit. If we make a change that does create new threads or is just not, it's just not efficient, then we may as well have not done it. And the other thing is that all of this has to be taken with a pinch of salt, because we're still actually not in production yet, so we still haven't actually 100% proven that this is sort of fit for purpose, really, I suppose. But obviously confidence is growing day by day as we use it more and run more performance tests. That's it. So yeah, there's more info on my blog, and there's also all of the code from today's stuff was in the Ratpack demo on my GitHub account. So yeah, any questions at all? Yeah.
Did you consider using Vertex, which apparently makes the same thing and it's also based on NPM? So why you think the Ratpack?
So no, we didn't look into it, and no, I don't know. Sorry, the question was, did we consider using Vertex as well? No, we did not, and I think that's just, yeah, we didn't know about it. So yeah, it sounds interesting. So yeah, could look up into it. Yes.
You show an example of your main method on Phill app, something non-trivial, because I'm more interested in the complexity of the chain of handlers. You get this out of hand or something.
Yeah, sure. So the question was, can you show some code on the actual on the real application, something that's non-trivial? So I think actually I haven't got the actual real code here, but one of the things that you would find if you looked at it the handlers make sense. You know, it's very, very easy to actually understand that, and the learning curve for the handlers and mapping them to URIs is honestly like a drop in the ocean. It's fine. It really does make sense. The calls to the downstream systems are really complicated. So I touched on the fact that the DAO that I was looking at earlier on was one of them was cold and one of them was hot. So what I mean by that is that cold observables. Does anyone know the difference in between cold and hot observables? So a cold observable is an observable that will emit items or do its work when you subscribe to it. A hot observable is something that will, as soon as you create that observable, it's doing its job, and then you subscribe to it later on to get those events. Now, we were using hot observables the whole time, which is all fine. But then when we came to a situation where we had an observable that represented some work to save, we wanted to do some validation before. And so we'd do some validation and then throw an exception. And then we were under the assumption that that next observable would not get, wouldn't actually do its work. But because it was a hot observable, it was actually being invoked. That's kind of confusing to explain maybe, but basically you need getting the control for something even as simple as just an if statement can take days, you know. And if you're not, I actually think that probably Java programmers, just, you know, a Java dev like me is probably not as good as picking this up as, say, somebody who's maybe had experience with Node, who's used to the asynchronous programming model a lot better, and they would probably be able to pick this stuff up probably quicker than us. So yeah, there's definitely complexities there. Yes.
I had a question. I was just wondering about, I see you implementing the handler interface, yeah, and I've seen a lot of examples like that, and almost certainly to the point where some of them are ununderstandable. The main method is so big and it's not readable.
Yep.
Yeah. And in my mind, I say that's what testing. Yeah. I have to write code in this day. Yeah?
Mm-hmm.
So have you been using the handler interface to actually prefer that class to a more manageable, testable unit rather than the Lambda?
Yeah. So the question was about handlers and you know, whether or not you put the logic in the main method or how you split it out. I think that because the team of developers are used to JAX-RS and resources, I think that having that mindset, we have basically made the handlers fit that kind of model. So it's like, you know, we've got a you know, get entitlements, you know, API call. We have a get entitlements handler, and then, you know, the one that does the saving, the update entitlements or add entitlements or whatever, we have a separate handler for that. So our coding style is probably different to the other people's, you know, code that you've seen on there. So it's flexible enough that you can make it in a way that is nicely split out, I think.
Following on from that, the other bit I had was I've seen Ratpack sliced a number of ways with Spring, yeah, with a DSL, with Ruby, and I just wondered if you considered any of those when you did your. I know you dropped it, and you know, I use Ruby sometimes or dabble with other things.
Yeah, we didn't.
Did you give any consideration to some of the other ones? The DSL looks clean. Right?
Yeah, sure. So I think that we didn't look into that because there was no one really on the team that was sort of, you know, really into Groovy, and that's probably the only reason that we just didn't look into it. If there was someone on the team that said, hey, look, we could do this way better in using the Groovy DSL, then, you know, maybe we would have done it. But yeah, that's my answer. Yeah. Yes.
Is Ratpack an approved technology in Sky? I know this is a hot question, meaning it took me like a month to get approval for RAP-STP, for example.
Right, okay.
A month of endless meetings.
Yeah, sure. So we went through tech governance, and there were a number of sort of things that we had to persuade that it was, you know, it was okay. So a number of things were that, you know, it's packaged just like any other application. Although it's experimental, it is at version 1.1.1, so, you know, it's maybe, you know, it's saying that it's ready for production. The other thing was that we can get support for a lot of other interesting things that you only think of later on. So one of the things that I find really fascinating is that we have a standard of the Sky request ID header. So this is a kind of like a unique ID that's assigned to every single HTTP request, and the logging at any point should log that out. How does that work when you have one thread that can handle about 10 different HTTP requests all at the same time? And there's a fix for that. So you can actually ensure that all of that stuff works. So yeah, I suppose there's that support. The green light for us to go ahead and use Ratpack, I think, was basically based on the fact that you're going to know before you go live if it's fit for production with the non-functional tests that you hit at it anyway, and because it meets all of these other standards, and providing we can integrate with App Dynamics and the other stuff, then it should be okay. So no, I think it's really good that we managed to get the sort of provisional green light. Really, I think it's a good testament to the being up for innovation.
It's a provisional green light.
Yeah, I suppose so. I mean, there were no objections, and I think that maybe it was a provisional green light on the basis that we're not going to be reckless, and we aren't going to go to production if we have any sort of serious concerns. So I suppose there is that element of trust in giving us that permission, that we don't just deploy it and have our fingers crossed. We need to be obviously really sure that it is fit for purpose before it does get deployed. Yes.
Have you tried integrating Hystrix with it? In the
yes. We have, yeah. So Hystrix integration, that was difficult, but I think it just came at a time when we were learning the asynchronous model anyway. Hystrix is amazing because the standard sort of support, I think, is the threading model. That you have a big thread pool, one thread per HTTP request downstream. If we had to do that, there would be no point in using Ratpack, because if you make 200 requests downstream, you have to spin up 200 requests. Then the bar graph that I showed you earlier on of the number of threads would then suddenly be that much higher, and it would be rubbish. So Hystrix does actually support semaphore. The same thread can be coming in and dispatching lots and lots of HTTP requests at the same time, and it can still keep track of all of that. Yeah, that was really, really useful. And actually, there's even documentation on Ratpack's website on handy sort of little libraries. So it seemed like a well-trodden path, and we haven't had any problems with it other than just the asynchronous challenges that we've had anyway. Yeah.
Hystrix as well, reactive coding. We found there's a lot of thread locals in their code, so we actually have to patch Hystrix to make it reactive friendly. So you might find that if you actually look in Hystrix code, they're actually built to be
right. Okay.
Normal sync.
Right. Interesting. Yeah, because there are some settings that actually say something thread.timeout, and we were like, oh, it's not a thread, but then it says, oh no, don't worry, this is actually for semaphores as well. So it's
the semaphore route as well. We had to go patch it because we did massive load tests and found that actually the calls trying to interfere with each other.
Right. Okay. I'd be very interested to talk to you afterwards.
Sorry, but Hystrix was conceived to adapt synchronous blocking applications to non-synchronous blocking. So if you have non-synchronous blocking systems, you shouldn't consider using Hystrix. That's one of the things. So it goes much more beyond the circuit breaker pattern. So, and the question I have also following that is, the examples I see most of the time, Java 7 code, RX Java, is this a conscious decision, or why not to use Java 8 instead?
Oh, in the code that I was showing?
Yeah, instead of listenable futures, completable futures, and Java 8 versions of this library.
I suppose we tried to stay as Java 8 as possible. I think in some of the examples where I could have had a lambda, I've introduced local variables just for sort of like the ease of.
Well, then that doesn't mean the actual futures that Java 8 provides, which are non-blocking and asynchronous.
Right. Okay. Yeah. Sure. So yeah. So I think that we just decided that we wanted to use. We could have looked into alternatives. I mean, the decision to use RX Java's observables, maybe we should have spent more time on that. Someone did actually make the point that, well, the onus should be on, choose the default that comes with Java 8, and then if it really isn't up to speed, then look into other things instead. But I think that the decision was kind of made. Yeah, maybe we didn't make quite the right decision on that. I mean, the Hystrix is obviously using observables, so I suppose that was one of the things that made us think, well, we're going to have to kind of learn observables anyway in our code base, so may as well, sort of carry on. But yeah, no, it's definitely not something that's set in stone. Yeah. Yes.
A question. I was curious. You talked about how many threads that Ratpack uses, and said that the default config was 2 threads per core. Why 2 threads, not 1 thread?
That's a really, really good question. So yeah, I really don't know the answer to that at all. I think that maybe there is. I'm totally going to guess. I don't know if maybe there's a certain amount that, you know, if you are switching threads a little bit, maybe that is slightly better performance-wise than never switching threads. I don't know.
I was going to say, a lot of server-side CPUs have can process hyperthreading to 20 per core, so it would make it safer.
Oh, right, okay, maybe that's it then. Yeah, sure. Yeah, good point. Yeah.
Just to look at a play framework with Hacker, which might be a little bit more of a conventional way of doing this.
Right, yeah, sure, yeah. No, I mean, I think that this is so complicated, you know, reassuring yourself, oh yeah, it's Java, don't worry, is almost like, it's so different from any other Java that I've ever used. It almost feels like you're at the point where maybe it'd be better to just learn a completely different language and just...
You can use play framework with Java and Echo as well.
Right, okay.
Java, so
yeah, sure.
The Scala guys got that route, but supports both Java and Scala, and it's, I think Echo's meant to get around the whole callback hell.
Right, okay.
Theory, that's what they say.
Yeah, sure. Yeah, I mean, Ratpack's meant to resolve callback hell as well, and it's I don't know, hell, maybe nightmare. Is what we've got.
The play framework is a little closer to Spring, so maybe it's a little less jump than the Ratpack handlers mechanism.
Right. Okay. Sure.
Look out for you can always go back to Synchronous.
Right. Okay. Right. Interesting. Right. Cool. Yes.
So I'm assuming that what you're doing, are you rewriting an old system that we've been migrating?
This is a brand new system, but it's having some sort of, there's one service that's got a little bit too big, and so to sort of keep microservices, we're taking some out of the old.
I suppose I'm curious as how you will judge that this non-blocking approach will be better than the blocking approach you have.
Yes.
Based on, because from my experience, we're doing the same thing. We moved to non-blocking. We're doing some Scala. We're using Spray. We're comparing it to a system that runs on that's blocking. It uses Tomcat, so it does the old classic 200 thread.
Yeah, sure.
In JVM 6. In reality, of production, the load is about the same. It's not very high, maybe 600 concurrent requests per bot. And I don't see how we can tell what is simply the new approach or what is just say because we're using Java 8, the JVM 8 is much more efficient.
Yeah.
What is is it synchronous versus blocking, or is this the JVM is now very good?
Yeah, I know. So the question was, how do you judge the success of this? And I suppose the answer is to only truly judge like that, you know, that Ratpack has actually got you the benefit is you'd have to have two streams, one making the Drop Wizard application and then the other one using the Ratpack one, which is absurd, but that's the only way that you could do like the proper full sort of apples for apples comparison. It's a very good question. I don't know how to actually make that comparison as good as possible because, yeah, if you change just two things at the same time in any test, you don't know what's had the effect, do you? You're not a scientific approach. You're just like, oh, well, I reckon it's probably Ratpack, you know.
I mean, theoretically, the non-blocking should get you up much quicker at low levels. One thread, it's easier to manage than a full pool of threads, which have to maintain. But I'm always curious, when you hit the maximum limit of the box, what the hardware can achieve, are you getting the benefit from a thread from two threads?
Yeah, I really don't know.
It's a mark and then they sort of peak at the same point.
I don't know. I think we need more experience with NFT really. To but no, very good question there. Yeah. Yes.
Sorry, line of that question. I believe that one of the answers there that with these technologies you decouple capacity from response time. So when you are using synchronous blocking frameworks, the more your capacity, the more your load goes up, your response time tends to grow because basically you are blocking. You have one thread serving each request, and there is a limited resource there, and it needs to wait. But with these technologies, you totally decouple that. So even if your requests were taking, I think it's often example 3 seconds, you should be able to still take in a big number of users. Because in those 3 seconds, only a really tiny fraction is used for processing. You can still take the request.
Yeah. Yeah, no, it's interesting. I mean, yeah, hopefully, I think the goal is, if you've done it correctly, then that your only upper limit is basically the CPU performance of the actual machine, and then your application is CPU bound, which I've never had the experience of working with an app that's CPU bound. So
it feels like in theory, the idea is this non-blocking removes the overhead of cool bread pool maintenance, which under massive load, you should be able to squeeze just a little bit more out of the hardware that you're running on. But I mean, I've not found anyone who's tested that, apart from maybe Amazon.
Also, PayPal, when they switched over to Node, they did a lot on their performance testing when they switched over to Node.js, which is a very similar thing. Single thread non-blocking, like right.
Very interesting. Very interesting.
You might find that when you do this kind of route, if you have two slow I/O calls, which take half a second each, your synchronous route will take a second. But if you design it correctly and they're not reliant on each other, then going asynchronous suddenly will take half a second. These things are easily parallelizable. So when you code this way, your code just naturally becomes as optimal as it can be. And if you've got little chunks of code that will generally just operate one core of your CPU is not doing anything, suddenly you spread out all 10 cores and the response time comes down. Okay. So there's a number of things you get for free of industry.
So again, I'm getting the sense that like the capacity of the hardware, there might not be a difference.
No, so what you might do is, because maybe your system's not too busy and maybe you're using 5 cores maybe in the morning or something, and suddenly one person's request may now actually spread over all 10 cores theoretically, so their response time will be down, then everybody's response time is going to be down, so it's just a more reactive application that you're going to get. But once you hit your CPU, you're not going to get more than 100%.
Okay. Any more at all?
Cool. Thanks very much, Phil. It was a great talk.
Okay, cool. Thank you. Thanks.